The third talk will be by Natalia Herrera Valencia, a PhD student at the Heriot Watt University. And the talk is entitled Unscrambling Entanglement Through a Complex Medium. Please go ahead.
Thank you, Jorge, for the introduction. Let me just share my screen. I hope you all can see it now. So, well, I would like to thank the organizers for inviting me. This has been an amazing workshop, and I'm very glad to be part of it. And thank you all for tuning in. So I'll be talking about a work that has been done in the BBQ lab at Heriot Watt University. And it was done along with Suresh Goyal, Will McCutcheon, our external collaborator from the University of Glasgow, Ugo Defiant, and my supervisor, Mehul Malek. Now, let me first do some advertising of our research group. We are the Beyond Binary Quantum Information Laboratory, the BBQ lab, an experimental quantum photonics group led by Mehul Malek at Heriot Watt University in the beautiful city of Edinburgh. So for more details and information, please check out our webpage. Now back to business. Well, for all the talks that we have heard, it's very clear that we're in the midst of a technology revolution that is being led by the control and engineering of individual quantum systems. And we've already seen great achievements on quantum communications, quantum computing, and quantum sensing. So in these rapidly advancing fields of quantum technologies, photons are the ideal carriers of quantum information. They are fast and cheap to produce. Their lack of interaction with the environment makes them very robust against noise, and they can be efficiently transported through fiber or free space. Now, in a big picture, we can think of photons as quantum optical interconnects, linking nodes of a global quantum network. Most of the photonic implementations rely on qubits, that is, encoding information in the degree of freedom of polarization. However, as we've already seen in some of the talks in the previous days, photons are naturally high dimensional because of their spatial structure and their temporal structure, which allows us to then access a D-level quantum system for encoding information on states composed of superpositions of spatial modes or of temporal modes. Photonic entanglement is a key for developing device-independent security for quantum communications, fault-tolerant measurement-based quantum computation, and even is allowing to have new approaches of imaging with quantum states of flight that could surpass classical limitations. Entanglement is a phenomenon that implies that a global composite system cannot be described by the product of its individual parts. Is a quantum resource for tasks that cannot be performed classically, and hence is very important to know how to generate it, how to measure it, and how to quantify it. Entangled systems have correlations on the physical properties. So, for example, we have two photons. They can be entangled in their polarization, and we can write them in the horizontal and vertical bases as such. And as we perform measurements on these bases, we can see that they are perfectly correlated. That is, both photons would be there on the horizontal state or in the vertical state. If we then do a basis rotation to a complementary basis to the horizontal and vertical basis, which is a mutually unbiased basis, the diagonal and anti-diagonal basis, and we write our state in these bases, we can see that we can also see correlations, perfect correlations. Now, this is precisely the signature of entanglement. Now, we can observe correlations in complementary observables represented by mutually unbiased bases. Making the step from qubit entanglement to high-dimensional entanglement with realizations, for example, with orbital angular momentum or with the time-frequency domain is interesting because these type of states allow us to achieve higher information capacities and robustness against noise. Problem is that precisely because of the large dimensionality of the system, the challenge here is to achieve an efficient generation, measurement, and transport of high-dimensional entangled states, being the latter the one that I will be concentrating on. But first, let me tell you how we generate and characterize high-dimensional entangled states in our lab. So we generate pairs of entangled photons through a spontaneous parametric down conversion. Now, our photons are entangled in their position, momentum, degree of freedom. And we perform measurements on them using discretized transverse position basis, which we call the macropixel basis, which is composed precisely by circular macropixels, that is discrete regions in space, as the ones that I'm showing. And so by making the photons incident on spatial light modulators, where we displace precisely these diffractive holograms, that, like the ones that I'm showing, we are able to measure the probability of our photons to be on selected modes. Now, scanning over these modes and measuring correlations between Alice and Bob, we can determine the correlations between, measuring the coincidence between Alice and Bob, we can determine the correlations of our state in these discrete position bases and in any of these mutually unbiased bases, which is constructed, each of the states are constructed as a superposition of these macropixel modes. Now, think of the macropixel basis and these mutually unbiased bases as an analogous to the two-dimensional case of the horizontal vertical basis and the diagonal anti-diagonal basis. They are complementary observables. Now, if we scan over these mob states and we measure correlations, as we have shown in a previous work, we are able to lower bound the fidelity of the state that we produce in the lab compared to a target entangled state, and in this manner certify the dimensionality of our state. Now, if we use measurements in all mutually unbiased bases of a given dimension D, we are able to estimate the exact fidelity of our entangled state to a maximally entangled state. This has recently allowed us to achieve the assumption-free certification of high-dimensional entanglement with a record quality, where we achieved the fidelity of 94.4% to a maximally entangled state in a 19-dimensional subspace. This fidelity allows us to certify that our state was 18-dimensional entangled and had an entanglement information of 3.8 bits. We achieved also a record dimensionality by performing measurements in two mutually unbiased bases on a 97-dimensional subspace using, for example, this is how the bases look in that big space. And we can certify in this way an entanglement dimensionality of 55. Now, it's clear that we can generate very large high-dimensional entangled states, and we can actually perform efficient measurements on them. But what happens when we try to transport them? Even though qubit entanglement has been distributed over free space and fiber over several hundreds of kilometers, high-dimensional entanglement transport remains a challenge because of the complexity of the channels. Now, what I mean is that effects such as atmospheric turbulence or mode mixing in fibers have detrimental effects on the delicate correlations that our high-dimensional entangled states have. Now, what is our approach to tackle this? We put disorder to work. What I mean is that complex scattering media, think for example, a sugar cube or a layer of paint or a multimode fiber, involves the complex interplay of hundreds to millions of modes. However, they're only linear optical networks, and hence control over those networks can make complex scattering channels a very interesting platform for the transport and manipulation of high-dimensional states. Scattering channels are characterized by transmission matrix. This is a matrix of complex coefficients that determines how each input mode scatters into all of the output supported modes of the medium. Now, the knowledge of this transmission matrix is key to achieve the control of light propagation through the medium, because this has been achieved classically with spatial light modulators that allows us to prepare input classical modes I and make them go through a medium and then measure the output in the J modes. Now, scanning over the input I modes, one can determine a D times D matrix that characterizes the medium. Now, what happens if instead of sending these classical input modes, we use instead a quantum state, a high dimensional entangled state as the one we can produce in the lab? Consider, for example, a 7-dimensional entangled state that is very close to the maximally entangled state, and where we can see very strong correlations in the pixel and the mutually unbiased basis. If we then take one of these parties, let's say bulb, and we make it go through a commercial multi-mode fiber that supports around 400 modes, when we measure the correlations as before, we see that they're gone, no correlations, and hence no entanglement can be certified from this. However, this output scramble state is actually carrying information of the channel in which it's traveling through, is this channel, the multimode fiber. This idea of the duality between quantum states and quantum channels is formalized by the Choi-Jamilkowski isomorphism, which says that statements about a channel characterized by these coefficients are mapped into statements about a state. So we decide to apply the channel state duality using the entangled states that we have in our lab to characterize the channel by measurements on the output and scramble state. So as I mentioned before, even though we don't have any correlations here, these measurements are actually giving us information of the transmission matrix of the channel, in particular, the amplitude of the complex coefficients of this transmission matrix. Now, what we need is also the phase information. So how do we obtain it? Well, we use our discretized position basis to perform measurements along with a co-propagating reference. So by interfering this reference that has a given phase theta r, we can, through phase stepping of this theta r, determine a matrix S that carries information about the transmission matrix T, but it's also carrying information about how the input modes scatter into all of the, like how the pixel modes is scattered into the reference and vice versa. So in order to have T, we need to also determine the matrix E. We can do it using the same trick. In this case, we have analyzed just the reference mode, and above we have our pixel mode and the co-propagating reference. And phase stepping over it, we can calculate this diagonal matrix E. Now, with the knowledge of both S and E, we can calculate the transmission matrix of the fiber T, that is both the real and imaginary part. Now, with this information, we are able to reverse the effect that the fiber has on our entangled state by, for example, applying the inverse transformation on the photon that goes through the fiber. However, maximally entangled states have an interesting property. They allow that operations on the state can be equivalently expressed as operations applied on either of its sides. So in this case, we could say that instead of unscrambling Bob by applying the inverse on Bob's photon, we could instead scramble Alice's photon and then recover entanglement by only manipulating the photon that actually doesn't go through the medium. Now, how does this technique actually look in the lab? Well, as I said, we have a photon, we have an entangled state, one of its photons goes through the fiber, and then on Bob's side, we use our pixel mode, but on Alice, we used a new basis, a scrambled basis that has the transmission matrix encoded into each of the states. Now, measuring correlations between the states, we can see that they are recovered, and we have, again, a very strong diagram. So as I said, we use the T to encode information of the scramble basis. We have correlations in one basis, but as I said before, entanglement can only be certified if you have measurements in at least 2 mutually unbiased bases. So how do we perform measurements in these mutually unbiased bases? We just rotate our transmission matrix using the transformation M, which is the mutually unbiased transformation. These allow us to measure correlations in all 8 bases on a 7-dimensional subspace, all 8 mutually unbiased bases, and you can see we recover correlations in every single one of them. Now, these measurements allows us to calculate a fidelity to a target entangled state in 7 dimensions of 84.4%. This fidelity allows us to certify that our output state is 6-dimensional entangle. So we have recovered high-dimensional entangle after the photon has gone through the fiber. So as a recap, we characterize our complex medium by imprinting all the information of the transmission matrix onto a single high-dimensional entangled state. We use this transmission matrix to reverse the effect of the complex scattering channel that the fiber is, and we're able to transport high-dimensional entanglement through the fiber. Interestingly, we can do this by only manipulating the photon that doesn't go through the medium. I would like to thank our funders and my collaborators in this project, Suraj Kaur, all Bristol's gang, Will McCutcheon, our collaborator from the University of Glasgow, Ugo Tafian, and my supervisor, Mehul Malik. Please check out our work on the archive, and thank you very much.
Thank you very much, Natalia. We have time for quite a few questions. I'm going to start with one from Francesco Graffiti. The question is, how stable is your transmission matrix over time?
Okay, good question, Francesco. Well, we observed that if we have, we put our setup inside of box that maintains a temperature stable, we can have a transmission matrix that remains the same almost for, we notice even for 2 weeks. Now, for example, we're running measurements in our lab remotely, and the quarantine has helped a lot for this. So we haven't had to manipulate anything, and our transmission matrix is the same and remains stable for now already a few weeks.
Okay,
but if you twist the fiber, then he's gone, and then you will have to measure.
Next question is from Rowan Hogarth. Sorry. How many measurements would be needed to characterize the channel sufficiently?
So it depends on the input entangled state that we have. So we use 7-dimensional entangled state. So that means that we had to recover a 7x7 transmission matrix. Now, this was recovered by taking correlations. So 7x7 matrices with the phase stepping. So multiplied by 4. Then we had to do the same with the E, and then you just calculate the T. So it's pretty much it's the same amount of measurements that you will have to do classically, also by preparing different input modes. But the difference is that we don't have to prepare different input modes, but we just have the high dimensional entangled state, and we can do everything with that single state.
Thank you. Next question is from Davide Bacco. How do you couple your high-dimensional quantum state to the multimode fiber?
Oh, well, it's just we have an objective lens, 10x objective lens, and we just couple light through it with our mount. There's no particular way that like we just couple until we get maximum efficiency. Now, when it goes through the fiber outputs and then comes and get measured through the SLM, and then we have to couple that light through it, the efficiency is only of around 5%, but that's enough for determining the transmission matrix. And just as actually it's a relevant question for example, this, you can see this is scramble measurement. You can see that there's a strong mode here that light goes through, and this is precisely of the way that we couple, because for aligning, we have to select a particular mode, which is close to this particular pixel mode. And so you can see it's kind of a bias of how much light is coupled effectively through it.
Okay, thank you very much. And in interest of time, I'm going to move to the next and final session of final talk of this session. Thank you again, Natalia.